Welcome to CMU 15445-645, Introduction to Database Systems. My name is Andy. I'm the instructor for this course. As I said on Piazza, I can't be in Pittsburgh right now. We are getting ready for Matt's cage fight on Wednesday, so we had to be out here in LA to prepare for that fight. So rather than just not having classes this entire first week, I wanted to record this while I'm on the road, post it online, and then that way, when we start having in-class lectures next week, right, we can get started on the good stuff. So before we get into today's lecture, I first want to talk about how Oracle is helping us out this semester with course development. So Oracle is actually one of the first relational database management systems that came out in the 1970s, and I'll explain what a relational database is in a few slides. So again, it was one of the original ones, but it's still widely used and sold today, right? It's probably the second most deployed database system in the world. It's certainly the most deployed commercial system in the world. And so even though it's from the 1970s, and there's other systems from the 1970s that are still sort of around, Oracle is actually still under active development, and they're adding a lot of interesting new modern features to it. So this course is about what I'll call it maybe traditional database management systems, or classical design. And it'll be interesting to see when they come at the end of the semester to give a guest lecture and talk about some of the stuff that they're adding to Oracle today, how they sort of go beyond what we'll talk about in this course and start looking at more advanced topics. So for this lecture here, I want to first talk about the overall outline of what's expected in the course for you as the student taking it. And then we'll finish up giving sort of a half lecture on the relational model and the relational algebra. And this sort of be the background that you need to have for the various topics we'll discuss throughout the rest of the semester. So if you're a student at Carnegie Mellon, then probably the foremost thing that's on your mind is the waitlist. So unfortunately this year they gave me a smaller classroom in Margaret Morrison than I wanted, so that means we can't take a large number of people. I think it says the max capacity is 100. I think it's like 96 is in the room. We can flub that number a little bit, but I mean the main takeaway is here we can't accept everyone. So the wait list now I think is 150 when I checked earlier today. So unfortunately, that means that if you're not enrolled in the course at this point, the likelihood that you're going to get in is very low. I mean, people will drop the course over the next week or so, and then we'll take people off the wait list. But unfortunately, I just can't take everyone. So you're more than welcome to audit the course. Just let me know that you're auditing, but we can't officially hold that many people. So the way we will enroll students as current students drop out will be just on your waitlist position on S3, on the registrar's website. So again, I'm sorry, but everything's available online, so you're more than welcome to follow along if you want. All right, so 15445-645 is, at its core, the course is about the design and implementation of database management systems. So that means that this is not a course on how to use a database to build like an application, like a website or something like that, or how to administer a database, how to deploy one, set one up. We're not doing any of that. We're really focusing on how do you actually build and design the software that is a database management system. So if that's not what you're looking for, if you're not looking to know how to build a database management system, then there's two other courses that you should consider at CMU that are outside of SCS. And the one in particular you might want to look at is 95703 at the Heinz College, which I think is information systems. And again, that's about how to set up and administer a database management system, but you don't really understand, they don't really go into details of how you actually build the software. The other thing too that people often ask is about, used to be another course at CMU, 15415, 615, something that I and Professor Christos Faludis has taught in the past. That is not being offered this semester. I don't know whether it's going to be offered in the spring, probably unlikely. So right now I think the only courses available in SCS would be this course, 445, and then 826 in machine learning or cross-clustered with the CS department. So again, there's only Christos and myself. We can't teach everything. So unfortunately, there's no other database class other than this one. All right. So the course outline is that we're going to be going through and discussing how to build a disk-oriented database management system. And I'll explain what a disk-oriented system is in a few lectures. But basically, we're just writing data out the disk. We assume the database is on disk. So it's sort of broken up. The outline for the topics we'll be discussing is broken up sort of into layers of the system, right? So we'll talk at a high level what relational databases are, and then we'll talk about how to store them, how to execute queries on them, how to run transactions on them, how to recover them if there's a crash or if we need to restart the system. So up to that point, up to recovery, that's the core knowledge you need to have to understand how a database management system works. And then from there, we can then build on that and start talking about more advanced topics like distributed databases or various other types of databases that are out there, or extensions of relational databases. So again, like the way to think about this is we'll go through every single layer of how to actually build the system, and we'll finish up with recovery. And so at that point, that's the basic you need to understand of how a database system works. And then we'll talk about how to extend them to scale them up or scale them out, or running them in the cloud environment. So right now the course website is online along with the syllabus and the schedule. So the basic outline, there should be a lecture twice a week, and then with each lecture there's readings that go along with it that are supplemental, that extend the kind of things that I'll be talking about, as well as also provide some course notes, which I'll mention in a second. So at all times, please refer to the course webpage. That should be up to date. Have the most up to date information on what's going on. So, unfortunately, we always have to talk about academic honesty. I'll go a little bit more detail what I mean about this as we go along. But when you ever have a question and you don't know maybe what the right thing to do is, please contact me so that we can discuss whether what you're doing could be considered plagiarism or stealing somebody else's work, right? So in general, again, this is an advanced course, so everyone should be aware that you don't copy code you find randomly on the internet. You don't copy from each other, but just be very careful because we will check for these things. And as I said, all the discussion and announcements for projects, lectures, homeworks will be on Piazza. We'll do grading with GradeScope. Your final grade will be posted on Canvas because that's what CMU wants, but the day-to-day discussion will be on Piazza. And there's a link on the course webpage now that'll take you to our page. There is a textbook assigned for this class, Database Systems Concepts. So this is actually a new edition that came out this year. I've looked at pretty much every single database systems textbook that's out there. In my opinion, this one's actually the best one. It's the most up to date. And as I said, I'll provide lecture notes for topics that aren't covered in the textbook. I have to admit, I haven't looked into detail of the 7th edition to understand how much it differs from the 6th edition. So if you want to get the 6th edition, I'm fine with that. I don't think there should be any major difference. I just may not know exactly how to. You can look at last year's course and see for the different topics what the chapter numbers, because they have changed. And I'm actually not sure whether you can buy this book anymore. Like, you can't buy it as a bound book. They sent me, a bunch of loose pages with three ring hole punches in them. So I don't know what the bookstore has. I don't know whether it's available online. The 6th edition is probably good enough, right? We won't be doing any homeworks or any problems out of the book directly, right? We'll provide everything for you. All right, so the breakdown for your grade in the class will be the following. So homeworks will be 15%. Then it will be course projects, which I'll discuss in a second. That'll be 45%. So for those of you that are CS undergrads, because the project grade, your final grade is comprised of 45% of projects, that's why this course counts for the system software elective for the CS undergrad curriculum. And then there'll be a midterm and final exam both at 20%, and then there'll be an extra credit, which I'll announce in a few weeks, when you can get an additional 10% bonus points. And that's entirely optional. So there'll be 5 homeworks throughout the semester. The first one will be a SQL assignment. We'll give you a SQL-like database. You have to write some queries for us. But then everything after that will be pencil and paper, because it's sort of a way to work through the sort of more theoretical side of some of the things that we're talking about. But it'll be like filling out multiple choice, and then you just take a picture of it and upload it to Gradescope, and we'll provide grades that way. So again, the first assignment is SQL, just because we actually won't be writing SQL for the rest of the semester because the course projects don't require it. And I think it's just good for you guys to touch it at least once, at least more of the advanced stuff we'll talk about next semester. So again, it goes without saying, all these homework should be done individually as well as the projects, but I just want to emphasize this, that like you're not allowed to work in groups and try to figure things out. It's not like a theory class. All these assignments can be done and should be done individually. All right, for the projects, this is the one I'm pretty excited about. So throughout the course of the semester, you will build your own database storage manager from scratch. So you'll start adding pieces one by one and start building out a sort of full-featured database storage manager. So the key word there is storage manager and not a database system, because you're not going to be able to run SQL or have a query parser or planner, but you'll be able to run queries that are hand-coded that will provide you. So it's more complex than sort of like simple key value store, but it's not like a full-fledged system. So the key thing about this is that it's very important for you to keep up to date with the projects, because every project is going to build one after another. So you sort of have to have the first project working correctly in order for the second project to work correctly, and the third, and so forth. So this particular system that we're using this semester is written entirely in C++17. It doesn't mean we're using all the advanced features of C++17. It just means that it's not like the C++99, the sort of traditional C++ you may have learned in other classes. So because this is Carnegie Mellon, and I assume this is an advanced class, I'm not, and nor the TAs are going to be teaching you or teaching you how to write or debug C++. I sent out the self-exam on Piazza. If you feel like you're uncomfortable with the sort of the gnarly aspects of C++, then you should try to figure out how, try to start learning this stuff now. But you can't come to us as the TA's office hours and say, hey, what does this stack trace mean? This time is really spent to be discussing the sort of the more high-level important database concepts that you're trying to implement in your code. So all the projects this year will be implemented on this new academic system that we've been working on called Bustub. So all the source code will be released on GitHub. And of course, obviously, it won't have the implementation of the piece that you're supposed to implement, but you'll sort of fill that in. So at a high level, it's a disk-based or disk-oriented database management system that'll support Volcano-style query processing. Different parts of the system have a sort of a pluggable API so that we can plop in different, replacement algorithms, or different index data structures, or different logging schemes or control schemes. So it's designed to be that way so that every year we'll switch up the projects entirely and have it be different from one year to the next. And we'll slowly build out the system further and further with new features, new functionality, so that after a couple of years we'll have a full-fledged database management system. So you guys are sort of the first ones starting off with these first set of projects, and then next year we'll modify them, and it'll be different. Right? So for this reason, we can make it open source, because I'm not worried about people next year finding your crappy projects, implementations, and copying their code, because all the projects will be entirely different. So this is what I was saying before on the last slide, that you're building basically a storage manager. The database system doesn't support SQL at this point, and nor will it this semester. But you'll be able to write queries, but you'll write them in sort of physical operator form rather than in SQL and then translate them, because it's not something we're doing just yet. So the name of the system is Bustub. I will explain offline what that means, but we had a nice logo made. And again, we'll announce this on GitHub. We'll post it on the link on Piazza in a week or two when we announce the first project. So we're pretty excited about having this everyone work on this semester. All right, for the late policy for the homework and projects, every student is allotted 4 slip days. So basically, for any homework or project, you say, if I'm a day late, you can decrement it from your count. So it'll be on each homework and in the project submission, you just say how many late days you use, how many late days you have left, so sort of allow yourself to keep track of how many late days you have. So After you run out of slip days, then you'll lose 25% for on the assignment's total points every time. It's for every 24 hours that it's late. So again, we'll just keep track of this as we go along in the semester. Obviously, if there's medical conditions or other issues that come up, please contact me and we can accommodate you. So again, as I said before, all these projects and the homework should be done individually. They're not group assignments. You're not allowed to work it out together and submit a single submission together. You should be doing everything individually. Now, some code for some projects may be still online from previous years. Don't take that. We're going to run it through MOS, the plagiarism checker. If we catch you running their shitty code, unfortunately, we got to report you to Warner Hall. So don't do that because it's stupid. It'll fuck up your life and it makes everything harder, right? Just don't plagiarize, okay? And again, if you're unsure, check the CMU's academic policy or policy for academic integrity, or contact me if you're unsure about what to do. And this includes also for the extra credit. And just because it's extra credit and it's optional doesn't mean that you can't also get caught for plagiarism. So don't do that as well. And I'll remind you every single time we put a new project out, every single time we talk about the extra credit. Okay? All right, so if you want to go beyond the kind of things we're talking about this course, if you really like databases, which I do, you have no idea how much I love databases. If you want to go beyond the course material, there's two sort of ways to get involved in database research or other database topics going on at Carnegie Mellon. So the CMU database group has our weekly meetings on Mondays at 4:30 in the Gates building on the A floor. And this is other students, visitors from companies and people in Pittsburgh or from abroad coming and giving talks about what the kind of research or kind of work that they're doing. If you want to get involved in the development of a sort of advanced system, we have our team meetings on Tuesdays at 12 o'clock, also in the Gates building. So we're building, in addition to Bustub, Bustub sort of the academic system, we have a new sort of full-featured database management system that we've been building for several years now. That, again, if you want to get involved in this kind of stuff, you should come check that out. And I'll send a reminder on this piazza. I will say also, too, if you want to take the advanced class, 15721 in the spring, all those projects are based on this other system we're building. So if you want to get started on that and sort of learn how that system works and get involved in the early days of this thing, by all means come to this. Okay. So with that's it for the course. And again, please, if you have questions about things, post them on Piazza and I'll respond. All right. So now let's talk about databases. The databases are super important in real life because they're used everywhere. So pretty much every single complex or any computer application you can think of, at the end of the day, deep down inside of it, there's going to be a database, right? If it's a mobile phone application, if it's running your desktop, if it's a website, right? If it's some kind of complex computer simulation, at the end of the day, there's always a database. Everyone has database problems. Many things can then just be reduced down to database problems. So a database, the definition I like to use is that it's a collection of data that's related together in some way that's trying to model some aspect of the real world, right? It's not just a bunch of loose files you have randomly sitting on your laptop, right? In some ways it's a database, but it's not really a useful one because you can't ask questions about it. So this data is usually related together or have some common theme to them, and it's trying to model some aspect of something that's going on in reality. So the example I always like to use for this class is that, say we want to have a digital music store, right? Something like Spotify or the iTunes store, right? And so backing this application will be a database that's going to keep track of the various artists we have and their albums, right? So what we would put in this database would be basic information about their artists and then information about what albums that those artists have released. Right, so that core right there, that's a database. So let's see how we actually could build now an application that could store this information. So let's say that we don't know anything about database management systems, right? We don't know about MySQL, we don't know about Oracle, we don't know about Postgres, we don't know about any of that. So in our own application, we're going to write this code ourselves. So the simplest database we could implement and manage in our application would be just one where we store our data in a bunch of comma-separated value files, or CFV files. And then in our application code, we're going to write the procedures, the methods to read this data and extract information we need to answer questions or queries for them, right? So the way to think about this is like for every entity we have in our application or in our database, like the artists and the albums, we'll store them in a separate file, like artists.csv, albums.csv, and then we'll have some code that knows how to open that file up, parse each line to extract the different attributes about, that these files are storing. Right. So let's say again we have two entities in our database. Right. We have the artist. An artist has a name, a year, and a country, and then we have their albums. We have the name of the album, the artist that put out the album, and the year that put it out. Right. So again, if we're just storing this as CSV files, we would have quotation marks for each attribute, and then commas that would separate them. So let's say now we want to write a query that could look at the artist, the artist file, and try to figure out the year that Ice Cube went solo. So Ice Cube was a founding member of NWA here in LA, and then he left them because of money disputes, and he went solo. So if we have this CSV file that has this artist information, we could write some simple Python code that would just iterate over every single line in the file, right? You would have a function that would parse it, just basically split each line up by its commas, and get back an array of attributes. And then we just check to see whether the first attribute equals Ice Cube, and if so, then we'll convert the second attribute to an integer because that's the year. We just print that out, right? Really simple code to answer this particular query. So there's some problems with this approach. So, we'll go through these problems of why you don't want to manage data like this in your application, and this will motivate for why we want to build a sort of general purpose or a database management system that can handle all these things. So the first question is, how can we ensure that in our application that for every single album that an artist puts out, the artist field in that album file is guaranteed to be the same? Like, how do we know that we don't have a spelling mistake for Ice Cube, right? And then if we end up doing that, how do we, if say Ice Cube changes his name, how do we make sure we fix all those things, right? The next issue is how do we ensure that the data we're storing is valid for the different type, right? So the album year should be a 4-digit number, but what happens if someone puts in a random string in that place, right? Anybody can open up the file and modify it because it's just a regular file on disk, but now our application does that parsing, and it sees a random string when it expects to see an integer, and it's going to throw an error because it's like someone modified this data in a way that was not expected. And then the next issue is, what if we have now an album that has multiple artists? Well, that's problematic because the way I set up my file, there's only one artist field, right? So I could try to store that within the quotation marks, a bunch of comma-separated values inside of that thing. But now I need to go look every single time I'm looking at the attribute and say, is the artist name an array itself, or is it just a string? So again, you have to write all the specialized logic to deal with these particular problems in your application. So implementing this is not easy, right? So how do we actually find a record? So I showed my simple example was a for loop to iterate and parse every single line to find the record that I was looking for. And so, my sample file had 3 lines, so that's not big of a deal, right? So that can be done pretty fast. But what if I had a billion albums? Do I really want to be opening the file every single time and scanning and parsing every single one to answer every single query? No, right? Because that would be really, really slow. Now, the next issue is that what if, say, our application that I showed here was written in it looked like Python code, But what if now I want to write another application that's written in another language, and then I want to use that same database? Right, so let's say that the example code I showed you was running on a web server, open up a file, parsing it, producing the answer. But now I have like a mobile phone application that wants to access the same database. Well, my mobile phone application might not be written in Python, might be written in another language. Therefore, now I have to duplicate all my logic to parse that file in my web app or whatever other application. And of course, now how do I start sharing things? Right, that becomes problematic as well. Right, so again, same thing. What if I have two threads or two programs, two processes running at the same time that want to write to the file at the same time? What's going to happen, right? If I don't do anything special, then the first guy will write something, then the second guy might just overwrite it, and I'll lose my changes of the first guy. So now I start losing data, or my data ends up being becoming invalid because it's getting garbled. So that's problematic. All right, the last issue is how do I ensure that my data is safe? So let's say that I'm updating a record, I open a file, I start writing to it, but then before I finish writing my update, the machine crashes, my program crashes. What happens, right? Should that update be there? Should it only be half updated? Right? How do I reason about what the correct state should be? What if I want to say, well, I don't trust the machine that I'm running on, so therefore I want to replicate my database, my files to a bunch of different machines so that if one machine crashes, the other one can just pick up and I can keep running without anybody noticing. And you say, oh, maybe I could use a distributed file system, but those things aren't general purpose usually, and that can be difficult to do. So for a variety for these problems as well as others, this is why you don't want to write the kind of stuff that we talked about of parsing a file and reading it in your application. You want to offload this, or you want all that sort of complex logic of how to manage the data in the database. You want a database management system to manage that for you. So a database management system is specialized software that allows applications to store and analyze information in the database without having to worry about the underlying details of how to do that, right? And it's software that can be reused from one application to the next so that you're not reinventing the wheel all over again. So a general purpose data management system, the kind of things that we'll talk about in this semester, are designed to allow applications to define, create, write queries against, update, and administer databases. Right? And for our purposes, we're going to assume our databases are stored in disks. They don't necessarily have to be, like there's in-memory databases or there's GPU databases or other things. Right? For these, we don't need to discuss those things yet, but just know that there's a variety of different databases out there that can do a bunch of different things or be specialized in different ways for a variety of applications. So again, I love databases a lot. I think about databases all the time. I love writing about databases or reading about databases. And you may think, all right, this is crazy. Why would anybody love databases or data management systems so much? So you have to understand, think about this. At CMU, we're a large school. We have courses in everything, right? And this course is for operating systems, coursing for networking, things like that. But database management systems are sort of a special class of software that are so important that there's full-time people like me that teach a course just on this, right? Like a web browser is important, but there's no class on how to build a web browser, at least as far as I know, right? Whereas databases are so prevalent and so widely used everywhere that and they're really hard to work implement correctly. That there's an entire course this course and talk about how to build it. So again, I think they're a unique piece of software or class of software that is definitely a hot area right now. At the end of the day, machine learning needs data. You store that in the database. So at every single application, as I said, at the end of the day, there's a database underneath it running, almost everything. So this is why a course like this, in my opinion, is super important. All right, so databases systems are not new. The first one came online, I think, in 1965 at General Electric. And people that are sort of in the early days of computing, the people quickly realized, hey, it'd be nice to have specialized software like a database management system that can manage large data sets for us. So you have to understand, back in the day, it's not like how it was now. In the early days, some things that we'll talk about in this course that we sort of take for granted now, because, of course, this is how you want to do certain things. Back in like the 1960s and 1970s, it wasn't obvious that this is the way to do things. So, in particular, the story I like to talk about is back in like the late 1960s, there was this guy, Ted Codd, who worked at IBM Research. He was a mathematician, but he got hired to work at IBM Research in New York. And he noticed that people that were working on databases spent a lot of their time rewriting their database application over and over again, because there was a tight coupling between the logical layers of what's in the database and the physical layers of how the data system was actually going to store it. So what I mean by that is, like, say you have a database and you want to store it in this database system, and you'd have to tell the database management system, oh, I want you to store this as a hash table, or I want you to store this as a tree. And then when you did that, it would then expose a different API for you based on what data structure you chose. But then now, say you change your mind, I told you I was a hash table, but I really want to run range queries on that. So now I want to do I want to be stored as a tree. So what you would have to do is dump all your data out, change your application code to now make calls for the tree API instead of the hash table API, and then you have to reload all your data back in, right? Because again, whatever you explicitly told the database management system how you wanted it to store the data. So Ted Codd realized that this was kind of stupid, right? This is problematic because people were basically refactoring the code all over and over again every single time there was ever a change like this. So now, back then, humans were cheaper than the computers, but you can easily see how this was not scalable. And nowadays, computing is cheap with Amazon and Microsoft and Google have the cloud computing, and humans are the expensive thing. So this problem is even more problematic. This issue is even more problematic today than it was back in the 1970s. But Ted Codd, quickly realized that people were wasting their time in fixing up software that they didn't need to. So what Ted Codd proposed was this thing called the relational model. So the first paper came out on this in 1969, but the one that everyone cites is this one from the Communications of the ATM that came out in 1970. So most people read the one that the relational model of data for large shared data banks, but this is sort of the seminal paper that sort of started the whole relational data model revolution of saying this is how you want to store data in systems. So this is very influential. And this is sort of the backbone of what we're talking about in this course. So there's sort of three key tenets of the relational model that Ted Codd proposed. So the first is that we were going to store the database in simple data structures as relations. So a relation doesn't mean like I'm related to my parents or whatever. A relation is essentially it's synonymous for a table. It's the relationship between the attributes stored in the tuple for that given table. So again, we would define at a high level that we're going to store all our tables or our database as these relations, and then we would access them through a high level language, meaning we wouldn't write the exact code that we'd want the data system to execute in order to retrieve the data that we wanted. We would just say, hey, we want you to compute this answer, please do it for me. We wouldn't actually say how to do it. So this idea was really revolutionary, because back then everyone was writing explicit procedural code. Here's the for loop to iterate through the table and find the data that I wanted. The example that I showed in the very beginning. This is how people wrote database applications before the relational model. This is actually pretty controversial at the time, because everyone was saying, oh, there's no way software can ever produce a query plan that's as efficient as what a human can do. Right? This is sort of the same argument that people made in the 1970s about compilers. They said, no compiler could ever generate machine code as efficient as handwritten assembly. And of course, nowadays nobody writes, or very few people write low-level assembly. Everybody writes in high-level languages, and the compiler does a pretty good job producing the machine code to execute it more efficiently than what a human could do. Same thing was said back then, right? The compiler, the database system couldn't produce a query plan as efficient as what a human could do, in which nowadays we have very complex query plans. The optimizers aren't perfect, but they can probably do a better job than what most humans could do. All right, and then the last key idea was that the physical storage or the physical storage strategy for a given database was left up to the implementation of the database management system. So again, we define our database through these high-level structures as relations, but how those relations are actually stored is completely up to the implementation of the database system. So the relational model doesn't say whether it should be in memory, should be on disk, how should we lay it out on disk, or how should we organize in memory. All that is transparent to the application. And so now the benefit of this is that if, for some applications, their database, may want to be stored in one way, and then over time, if the application evolves, it may be better to store it another way, and then we don't have to rewrite our application because we're still writing at a high-level language like SQL, and we're still accessing these relations, but underneath the covers, the database system can start moving things around for us, or changing its layout, or recompiling certain things, changing the data structures, and we don't have to change any of our application code. So we have a clean separation between the logical and physical layers, which is absolutely what we want. All right, so the relational data model is not the only data model, though. It's certainly the most widely used data model, and in my opinion, I think it's the best data model. But there's different data models for different types of workloads, and the relational data model is sort of a catch-all that can encompass a lot of things. It's not to say that the other ones are bad or wrong. It's just the relational model. 9 times out of 10, that's probably what you need. So the data model is the high-level concept of how we're going to describe the data in our database, and then the schema that we provide for a given collection of the data in a database is the definition of what we're actually storing in. So I'll show what I mean by this in a few slides, but the data model is essentially the high-level concept of how we organize the data, and then the schema is to say, all right, well, what is the data we're actually storing for this application for this given data model? So again, as I said, the relational data model is just one of several other data models. I'm showing a small sample here. Again, most database systems that you know about today and the ones we'll cover in this course, MySQL, Postgres, Oracle, DB2, SQL Server, SQLite, all these are relational database systems that use the relational data model. If you're familiar with the term NoSQL, the NoSQL systems are usually these key value graph, document, or JSON or column family data models. And again, I'm not saying necessarily that the relational data model is better than these other ones. There's certain application domains where some of these could better describe the data than the relational data model. And the relational data model has certainly adopted some of these some concepts or ideas from these other data models in newer versions of it. It's just, the relational data model can model all of these things. It just with varying benefit or advantages over the sort of the basic data models. All right, you can also store arrays and matrices. That's considered a data model. This is mostly what people use in machine learning. All right, there's some databases that can store matrices and arrays. They're not that common. People usually use like data frames or some other things. That would be an example of a matrix data model. The hierarchical and network data model or the multi-value data model, there's a bunch of these other ones. These are more esoteric. These are what the original data models were used in the 1960s and 1970s, sort of around the same time the relational data model came out. You almost never will see these things. If you're like a new startup or building an application for the first time, you definitely don't want to use any of these things. They're mostly in legacy applications. It's just the remnants of old software. I would say this is not necessary to even consider them. So again, for our purposes, we're focused on the relational data model. That's what we care about in this course, and that's what we're going to focus on. Because again, the relational data model can be used to model anything. So the relational data model is comprised of three parts. So again, the first is the structure of the relations. This is like the schema, how we're going to define what are in our relations, what their attributes are, what their types are, and so forth. Then we'll have the integrity constraints that will define to specify what is a valid instance of a database given the structure, given the schema we provide. And then we'll have a way to manipulate and access the data in our database, right? How do we actually run queries that can either extract information or modify the contents? So let's go back to our music store example and look at some concrete examples of what a relational model database looks like. So again, a relation is just an unordered set of elements or records that have attributes that represent instances of entities in our relation. So again, an artist has a name, has a year, and a country, and we can see in our relation example here, we have, for each record is sort of one row in this diagram, and we have all those attributes. So we would refer to a record in the relational data model as a tuple, right? It's going to be the set of attributes for that instance of an entity within our relation. So in the original the original relational model written by Ted Codd in the 1970s, all these values had to be atomic or scalar values, meaning they couldn't be arrays, they couldn't be nested objects, and so forth, right? You always had to be sort of, it's one string, one integer, one float. So again, that's what the original data model, relational data model, talked about. But in recent times, you now can store arrays, you now can store JSON objects in relational databases. Right? That particular restraint has been relaxed. Now, there's also going to be a special value in the domain of every attribute that we're going to store. They're called the null value. That means that the value is unknown. So that'll cause some problem when we start running SQL queries. But pretty much every database management system supports relational database system supports null values. But how you actually store them is left up to the implementation, and there's a bunch of different ways to do that, which I think is pretty interesting. All right, so then you understand the parlance. We'll say that a n-area relation is a table that has n columns, right? So I'll use the term relation and table interchangeably. They mean the same thing for our discussions. I'll say tuple, sometimes I'll say record. I'll try not to say row because that's something very specific when we actually start to talk about storage models. So, but all of those words can be used interchangeably as well. All right, so one thing we also have in a relational model is primary keys. So primary key is going to be a unique attribute or set of attributes that can uniquely identify a single tuple. So in this example here, we actually don't have a primary key for any of our attributes because there could be other artists called the Wu-Tang Clan. There aren't, but there could be, right? There's nothing in the world that prevents somebody from calling them that themselves that. So we can introduce a new ID field as a unique primary key so that if you're looking at the tuple with the ID 123, you're explicitly looking at the original Wu-Tang Clan. So in this example here, this is like a synthetic key that I've introduced into my relation, my schema here, right? In a real artist, they don't have an ID 123. This is something we're using in our database management system for this particular relation to uniquely identify the tuple. So there's different ways to generate these things. So there's some systems, at least in the SQL standard, you can automatically generate these auto-incrementing keys. So that every single time I insert a new tuple, there's some counter that increments by 1 so that that new tuple gets that unique identifier. Other systems, if you don't specify a primary key, internally they'll create one. They don't really expose it to you, but they'll use that to keep track of this is the particular physical record or physical tuple that you're looking at. Right? For this example here, it's a synthetic one that's exposed through the logical layer. So this could have been generated through an auto-increment key. There's also foreign keys in the relational data model. So a foreign key is a way to specify that an attribute from one relation has to exist in at least one tuple in another relation. So this is how you're going to maintain integrity across different relations, so that you don't insert things that map to unknown or non-existing entities in another table. So going back again to our example here, so we have the artist, we have the album, and so for the album relation, we may want to store multiple artists that could all collaborate on an album together. So we have this artist field now here, but in this particular example, right, for this mixtape, there's multiple artists, so I can't encode multiple values in the artist field because I said they had to be scalar. So instead, I'll make this separate cross-reference table here, where I'll have a foreign key reference from the artist ID that is part of this album, and then the album ID that they're involved in. So now I can store multiple artists on a single album. And the data management system will keep track of whether these albums and artist IDs actually exist in the real relation, so that prevents me from inserting an album that has artists that don't actually exist. Right? The data system can protect me from inserting bad data. And again, I avoid having to implement all that extra code myself in my application, which again relieves me from writing really hard code. All right, so now we want to talk about how we actually want to get data out of our database. Right? Again, I showed that simple example of writing the for loop, but I said that was a bad idea. We don't want to have to keep doing that for application. So what do we want to do? So the DML is a way to manipulate the data and either accessing it or modifying it in a way to produce the result that we're looking for. So there's two ways we could do this. So the first is procedural, meaning we'll specify at a high-level strategy of how the data system should find our particular result that we're looking for. So I don't mean exactly like the procedural code, the Python example I showed before, but just sort of a high level say, hey, this is what we want you to execute. The other approach is called non-procedural or declarative, and this is where we're going to say, this is what we want, this is the answer we want the data system to generate for us, but we're not going to specify how to actually produce it or actually how to go about and getting it. So we're going to say, hey, at a high level, do this, and we hope the data system can do it, figure out an efficient way to do it for us. So we're going to talk about now is relational algebra, and this is the example of a procedural language. And relational algebra is not hard to understand. It'll come up later on when we talk about query execution. But this is what Ted Codd originally proposed in the 1970s. A non-procedural example would be something like relational calculus. And so we don't need to discuss this at all, not because I don't think it's actually necessary, at least for our purposes in this course. But relational calculus will come up if we start going into detail about query optimization, because you have to use calculus to derive efficient query plans and do pruning and things like that. So again, for this course, we only need to focus on relational algebra. I'm just bringing up relational calculus to say that it exists, that it's out there. It's an example of a non-procedural language, but for our purposes here, we don't need it. All right, so Ted Codd proposed 7 fundamental operators in the relational algebra. So these are the fundamental operators we have to retrieve, manipulate tuples in a relation to produce the answers that we're looking for. So one important thing to mention is that this algebra is based on sets. So a set is an unordered list or unordered collection of data where you cannot have unique values. Now, when we talk about SQL is not going to be based on set algebra, even though it uses relational algebra as the underlying operators for doing query execution. And I'll explain again when we talk about SQL next time what that means. So the way this is going to work is that each of our relational operators is going to take in one or more relations as its input, and then it's always going to output a new relation. And so the idea is that we're going to compose complex queries by chaining together these relational operators together to produce the answer that we're looking for. So these are like the primitives you would use to do some operation on the data, on tuples, and then to produce a more complex query, we put them together. So we select, projection, union, intersection, difference, product, and join. So again, these are the fundamental ones, and we'll go through each of these. So the first one is select. Select is basically taking a subset of the tuples that satisfies some selection predicate. So you can sort of think of this as like a filter. You say, here's for a given input relation, here's the predicate that I want you to evaluate for every single tuple. And if it evaluates to true, meaning the predicate is satisfied for a particular tuple, we'll add it to our output relation for the select operator. So the easy way to remember this, the word select starts with an S, and so the relational operator is a sigma, which also starts with S. So you would say, I want to for this given input relation, here's the predicate to run and produce our output. So doing a real simple example here, say we have a simple relation, has two attributes, AID and BID, and so we could do a select operator like this that says, find me all the tuples where AID equals A2, and then our output would be a new relation with these two tables and the same schema or the same attributes as the input relation. I also can combine together using Boolean logic, combine together more complex predicates. So I can say where AID equals 2 and BID is greater than 102. And again, we're not specifying in the order in which you apply those predicates, right? Because it could be more expensive to do one versus the other. That's all left up to the data system to decide on its own what to do. So now, if you know SQL, the way we just write this in SQL for that second example, it's to think of the select operators as like the where clause, right? So you say where AID equals 2 and BID is greater than 102, right? That's a translation of this select operator into SQL here. All right, so the next operator is projection, and in here what we're doing is we're going to generate a new output relation that contains only a subset of the specified attributes from our input relation. Right? So you would say, here's my input relation, and then my projection is, here's the attributes that I only want you to emit, to produce in the output. And again, projection starts with a P. It uses a lowercase pi symbol, so it's super easy to remember which one it is. So again, here's our simple example with relation R with AID, BID. So in this case here, I can have I first do a select to just produce all the tuples of R where AID equals 2, and then now in my projection clause, I can say I want the BID value subtracted by 100, and then as well as the AID value. So I can reorder my attributes any way that I want, and then I can manipulate it in any way I want with any kind of arithmetic or kind of string function operator. So again, in SQL, it would look like this. So you have in the output clause of your select statement, you would say BID less than 100 and AID. And then the where clause is just what you did in the select operator. All right, union operator is where we're going to take two relations and we're going to produce a new output relation that contains all the tuples in either the first relation or the second relation or both of them. Right? You just combine these two relations and mashing them together. Right? So if you do the union on R and S, you get a giant. You're basically concatenating S on R as the output. And so for this particular operator, you have to have the same attributes of the same type in the two relations you're trying to union together. Right? So in this case here, if S had, if it had a third attribute, you wouldn't be able to take the union because it wouldn't match. So in SQL, there is a union all operator. So the union one is not exactly the same as the union operator in relational algebra. You have to add this all qualifier to get it to do exactly what you want to do. So again, we'll discuss what the difference of these two is in the next lecture. There's also intersection, same thing. So now what you're doing is you're taking all the for both the two input relations. You're just going to produce the output relation that has tuples that appear in both the two input relations. So again, taking the union R and S here, we'll just produce a single tuple that has, a single relation that has one tuple, A3 and 103. So again, you have to have the same number of attributes, the same type, and the same name in relational algebra in order for this union to work. And then there's the intersect keyword in SQL that will do the same thing. Difference is where you take all the tuples that appear in the first relation but not the second relation. So again, I can take the R The difference of R and S is just all the tuples that don't appear in S that appear in R. So in this case, A3103 appears both in R and S, and so it's excluded in the output, but A1, A2 don't appear in S, so they're in the output. And in SQL, you use the except keyword, or except operator, to perform the same kind of operation. All right, the second last one to do is the product operator. So this is also sometimes called a Cartesian product, or if you know SQL, this is, I think, called a cross join. So basically, you just want to generate all combinations of all tuples from the two input relations. So you're basically just taking the cross product of these two and just producing a giant output of every single unique combination of all of them. So again, in SQL, you use cross join, or if you don't actually specify that what the join is at all, you get this output here, like that. So you may think this is kind of stupid, and this is like what you not want to do. You never want to do this, but this actually appears sometimes in testing, some testing applications where you want to say, give me all the unique combinations of different configurations of the thing I'm actually trying to test, and this is a really simple way to actually do that. All right, the last operator to talk about is to do joins. So this particular join is called a natural join. It's not the kind of joins we'll talk about in the future, or not necessarily the type of join we're talking about in the future, but this is very explicitly talking about a natural join. So the way the natural join works is that for every single tuple in the out1 relation, you see whether it matches all the attributes in the other relation that have the same name, the same type, so the common values of them, right? So in this case here, if I want to do a natural join on R and S, I look at AID and see whether I find a match. I look at the AID in R, see whether I have an AID match in S, and then if I do, then I check to see whether I have also a BID match from R and S, and then if I do, then that's produced as the output here. So again, A3103 exists both in R and exists both in S, and it can produce the output. So in SQL, there's a natural join operator like this. Again, notice I'm not specifying how I want to do the join. It knows that I'm looking to see whether I had matches based on just the name here. So the reason why this is different than the difference is because there could be additional attributes in R and S that don't have the same name in shared across the two relations, and so they will actually be produced in the output. So the schema is allowed to be different as long as there's some common attributes that you're doing the natural join on. Where in the difference operator, you have to have exactly the same attributes of the same type. All right, so these are just the original main 7 relational algebra operators that Ted Codd proposed. Since then, there's been a lot of research and been a lot of additional stuff that people have added, right? Since, like, there's things like doing sorting or order pies, where we know we want to do that in SQL. The original relational model proposal doesn't talk about these things. Or relational algebra proposal doesn't talk about these things, but people have since extended the relational algebra and include these other ones. So doing rename, assignment, duplicate elimination, aggregations or group bys, sorting, division. So again, we may see some of these. We'll certainly see aggregations and sorting later on. Just to say that there's placeholder algebra operators that we may have to consider when we start doing query planning or doing query execution. All right, so to finish up, I just want to sort of point out one particular thing. So the relational algebra is still pretty high level compared to like our for loops as before, because we're not specifying anything about how the data is stored in terms of like its data structure and so forth. We're just saying it at a high level, hey, scan this table and do a filter, right? But it's still, at the end of the day, it's still kind of telling you what steps, in the order in which you should perform these steps. So again, let's say I want to do a join between R and S, and then I want to filter out any tuple where, only produce the tuples where the BID equals 102. So I have two examples of two relational algebra expressions to execute this query. So in the first one here, I do the natural join on R and S first, and then I do my filter on BID equals 102. And then in the second example here, I do the filtering on S first, where BID equals 102, and then I take the output of that relation, and then I do the natural join. So again, you may think at a high level these are the same thing. They're producing the same result, but the performance characteristics or the how efficient the data system will execute these two query plans can be vastly different, right? Like, say I have a billion tuples in R and S, and there's only one tuple in S where BID equals 102. So if I do the join first, I'm going to join a billion tuples with a billion tuples, and then I'm going to scan through and just find that one tuple where BID equals 102. Whereas in the second plan, I could do the scan on S first, find that one tuple where BID equals 102, and then now I'm joining that, that one tuple with the billion tuples in R. So again, even though we're not getting at the low level, like you run this for loop and do that, it's still specifying relational algebra the steps we actually want the data system to use to execute for our query plan. So what we really want to do is be able to just say at a high level, tell the database system, hey, this is the answer I want you to compute, and not actually specify how you want it to compute it. So I want to say, hey, go just give me all the tuples joined from R and S where BID equals 102. Didn't say whether you should scan S first or join with R first. I say this is the answer that I want. And the reason why we want to do this is, again, because now in our application, we just specify this high-level answer we want the system to compute. And if our table or if our database is really small today, and then it grows really big a year from now, I don't have to change any of my code. The database system could figure out, oh, well, you had a small database before. I want to execute it one way, but now you have a billion tuples in S, and maybe I want to do the filtering first. But I didn't have to change my application code to make it do that, right? The data system could do this for me. So this is what we're going to try to do by running queries. In particular, we want to run SQL. And so the key thing to understand is that although SQL is the standard way people express queries for run the relational model, it isn't the only way you could do this. It just happened to be the one that everyone uses and standardize on. And actually, when Ted Codd wrote the relational model paper first in 1970, he actually didn't even propose SQL. He didn't even propose any high-level language. He just said, hey, here's a relational algebra. He then later proposed his own language called Alpha that was a competitor to SQL in the 1970s. Of course, you've never heard of it because no one ever used it. And actually, in the 1970s, there was another competing language of SQL. There's another thing called Quell out of Berkeley for this system called Ingress, and they both look similar. Quell and Alpha and SQL sort of look similar to each other, but of course the syntax is very different. It just so happened again, SQL just sort of won out. It's what everyone uses today because IBM invented it. So the way to think about this is that, again, this is what I showed the very before. This is like the lowest level way you could actually execute this query of finding all finding when IceCube went solo. But instead, I could just write a really simple SQL query like this and say, this is the answer that I want you to produce. And then the data system could then figure out, oh, I want to write it in this particular for loop, because that's the best way to do this. And then if I add indexes, then the query plan could change, right? So the beauty of the relational model in SQL is that we can write these high-level queries that we want, and then over time, as the database changes, as the system itself changes, or our workload changes, it can adapt and improve itself without us having to go back or change our application. Again, for this reason, that's why I'm super excited about the relational model, and I think it's always the right way to go. All right, so just to finish up here, and again, I realize it's awkward for me sitting here in the bathtub giving you this lecture, so I appreciate you guys sitting through this. So databases are ubiquitous. Databases are super important. Databases are everywhere. So no matter what you do throughout your life, even if you don't go, if you don't go in the field of databases, you don't go in the field of computer science or computer programming, I guarantee you throughout the rest of your life, you're going to come across databases, and it's going to be important for you to understand how they actually work on the inside, right? Because when things aren't working the way you think to be working, you need to know, oh, it's written this way, this is what it's actually doing, so that you can figure out how to actually improve things. So we discussed the relational model, we discussed the relational algebra, and we showed how these are the primitives we could use to essentially use them as the building blocks to generate queries that we can execute on a relational database to update it and derive answers. So we'll see relational algebra again later in the semester when we talk about query optimization, query execution. But just in the back of your mind as you write SQL queries for the first homework, you should be thinking about, oh, well, how would, the database system is translating these into relational algebra, so to think about how it is actually doing it, how it actually execute these things. Okay, I almost forgot one last thing. The most important thing you need to understand about databases through the rest of your life is the following. When you look back at the 36 chambers, you understand who were the original 9 involved in it. You have the RZA, the JIZA, Inspector Deck, Ghostface Killer, Master Killer, You God, Method Man, Old Dirty Bastard, and Raekwon. But the other important thing too is Capadonna was in jail at the time, so he was actually an original member of the clan, but because he was in jail, he couldn't be on the 36 chambers. So that's the most important thing you need to understand throughout this entire semester. Okay? All right, guys. See you next time.
Oh yeah, coming through with my showering crew. 2 cents for a case, give me St. Nas brew. In the midst of broken bottles and crushed up cans, met the cows in the jam, oh I'll try. With St. Nas in my system, crack another, I'm blessed. Let's go get the next one and get over. The object is to stay sober, lay on the sofa. Better yet, down my shoulder. I'll be damn stressed out, could never be son. Ricochet jelly, hit the deli for a cold one. Naturally blessed, yes. My rap is like a laser beam, the bones in the bushes. St. Nas spin like canteen. Crack the bottle up and St. Nas, sipping through gold. You don't realize the drinking ain't only to be drunk. You can't drive, keep my people alive. And if the same don't know you from a can of pain.